Hi everyone, my name is Martin Dallinger, and in this short video, I will introduce you to our simple, explainable AI framework based on fuzzy rules. With this project, you can find potential rules underlying in your data in natural language. This might show you that your dataset is affected by biases, like decisions that were made inconsistently or immorally or even maybe illegally in your company or in any dataset really, even with statistical tests. This project was created in close collaboration with Professor As at the Johannes Kepler University. And for more info, check out the GitHub project down below. And this is the domain you can find the project itself in. You can try it out yourself. There's even a demo dataset, which I will showcase in a few seconds. And as a short disclaimer, as of right now, this project only works for regression-based datasets. So if you have a numerical target variable, for example, in this dataset, we have the numerical target variable salary, and for all other datasets, you might be able to transfer it to a numerical dataset. For example, if the target class is binary, you can transfer it to 0, 1. And this is a small workaround here. Or if there's multiple classes, you can check out the differences between the classes. So there's different approaches to go. You can, of course, either examine your own dataset here and then set the configuration parameters, which I will explain shortly. Or you just try the demo dataset. I will not open it in a new tab since it's already open here, and go with the default config parameters essentially. So what do we see here? We see the framework in action essentially. So these rules are all automatically generated. There's a few pages, there's 372 entries of rules, which were already heavily filtered. So basically every possible rule which could be in the dataset up to a certain number of conditions is generated. Then there's some filtering applied, there's some reweighting, again filtering, maybe again reweighting. And then after a certain number of steps, these solutions emerge and they might hint at biases. Like here, we see if the gender is female and the salary is low. This is a very surprising rule in this hypothetical dataset. And we might want to check why this emerges. And it's even statistically significant. We can see here as the p-value is sufficiently low if we have a significance level of 0.05. And we can also sort by the p-value and see other statistically significant rules. Like if the experience is very low, then salary is very low. This is not so surprising. But if the hiring manager is B and if the gender is other, then the salary is high. This might also be surprising since the hiring manager B might have some sort of preference towards the gender other. So this is basically the framework. And let us now dive into the dataset to better understand this. So this is the dataset. We generated it as a hypothetical dataset. And here's the code. This is also on GitHub. But essentially, some basic rules which were applied were ethical and unethical. So as an example for an unethical rule, certain HR managers have a preference for the third gender, as we've seen before, which was discovered by the framework. As an ethical rule, we see that salaries increase with better grades or better university reputation or more experience. But we've also encoded in the dataset that women have less experience. And this in turn indirectly causes that women earn less in this hypothetical dataset. Also talking about gender, of course, this can in future work be encoded not as ternary, like men, women, other, but more fluently. And this is definitely realm of future work, but we wanted to keep it simple here. So looking back at the dataset, we discovered all of the biases which were encoded in the dataset artificially. There's of course many random components to this as well to make it a bit harder to discover them. And we even discovered the implicit bias for women to earn less in the hypothetical dataset. I would say this is very, very good that the tool found the implicit bias, which only resulted from other attributes, but somewhat back propagated to the females. You'd see that either something bad is going on in the hiring process or something bad is going on in general. It reflects societal biases as well. Okay. Here we also see that the random variable is included, but we also see that the p-value is really high. and thus there's no real big attention needed towards this rule. We can also check out the falsifications. So these are fuzzy rules, so they are based on degrees of membership. This is much rather defalsification, as this is the target variable, and we can see the degrees of membership. This is also used then for the output Mamdani defalsification, as it's called, but these are rather details. I want to just show you that you can see fuzzy sets, you can examine the memberships and the domain values by clicking onto the certain column names. And in this case, we model gender discretely, which might be changed in future work. So you cannot click on it. All discrete columns cannot be clicked on, which obviously makes sense. There is no falsification except for binary rule assignment. Of course, you might also want to search some rules. This is possible up here. So we can also see what happens to technicians. If job position is technician, we already see it. If experience is low and if job position is technician and salary is low, you might also get more hits. In this case, notice didn't change anything. Then salary is low. Okay, in this case, we mainly have compound rules about technician. We don't have rules only having the technician for reasons I will come to later when we analyze the configuration. Right. You can also download the rules in the JSON format, and you can observe the quality of fit. So the R-squared value here is particularly nice, and we've got a low mean absolute percentage error. This number here is rather big because the salaries are yearly, and so the numbers are just rather big, so the error is actually quite low. Let us postpone to look at the warnings later and now check out the configuration. These 3 parameters are just with respect to the CSV file. So you just set the split character as the semicolon here, the decimal character is the dot, and the target variable is salary here, which we want to explain. This has to be a numerical variable, as I already hinted at. This is the number of the maximum antecedent combinations. I would recommend keeping this low for computation time and so if you've got a really, really high multicollinearity, then this might be a problem for finding a good fit to the regression model. Take this into account and keep this number low. This means up to how many if parts you can have. So in this case, it's 2. So we have if experience is low and if something else happens, then the consequent appears. So since this rule is also automatically generated, the antecedent combinations has to be 2. This is also automatically generated because it's up to 2 different if parts, so to say, the 2 different antecedents. I would recommend using the intercept for the regression. This is just a default regression parameter. Here we can set if we want to compute the p-values, put an exclamation mark here, since it's a rather dangerous setting if you're short on time, I would say, because it can take really long. And I would set all other parameters first, run it, check if the output is somewhat good, and then compute the p-values and rerun the model again. Okay, the next part is for falsification. How many sets do we want? How many triangles do we want here, essentially? This can become more fine-grained, but you also, again, increase the linear dependence, but you decrease the error here, and you increase the granularity, so it's a bit of a trade-off. Same for the defalsification, basically for the target variable. All right. Now, with respect to the whitelist and blacklist rules, you can include certain rules. So you could include the rule if experience is low and if job position is technician and if gender is female, then something happens. And you could write it in here and still have antecedent combinations set to 2, although there are 3 antecedents in there. You can also set this to 0 in theory and just write your own rules in there, which you want to check. But of course, you need to put in many rules to get a good R-square value. You might also want to exclude rules and see how the quality of fit behaves, how different coefficients behave. This can be done with the blacklisting. And in case you only want your whitelist rules, you can tick this down here with only whitelist in the rule filters section. Speaking of the rule fitters, these two are a bit advanced here. This is also with respect to regression, and it's in the case where you have multicollinearity. So some columns are duplicates of each other or near duplicates. So certain rules might be, or certain samples might be near duplicates of each other. Of course, there's not much benefit in having them in, and you might want to remove them, and they cause the model to be less stable. So this can be tuned to get a more stable model, essentially. All right. Regarding the dependency threshold, is also an advanced value. It's for reducing the linear dependency between the columns, and it applies Gram-Schmidt orthogonalization on the columns if you want it. But I would set it to 0 in the default case, as Lasso already deals with it kind of well. And this is the significance level you can set to drop certain rules if you only want significant rules. So you can set remove insignificant rules, and if any p-value is above this significance level here, to just remove the rules. Right. Now coming to the rule priority filtering, this is a very, very important setting because this reduces many automatically generated rules, which are not so important. So this priority is computed in this section here, and it's a weighted sum essentially of the support weight, which is computed with rule mining techniques, and the leverage, which is also a rule mining measure. So the support shows in how many samples is the rule reflected. If we discretize the classes, the fuzzy sets, the leverage shows how surprising is the rule, how nicely surprising in a certain sense. So for example, in a supermarket, if 30% of the men, let's say, buy diapers and beer, and 30% of the men in general buy beer without looking at diapers, then it's no knowledge gained. The diapers is not the useful information. The leverage would be 0, but the support would still be 30%. So this is a measure of surprisingness of a rule. The diapers beer rule is not surprising anymore in comparison. Okay, this weight is the number of antecedents. So it's an inverse of the number of antecedents. Actually, we only have one antecedent, so we would take 1 over 1 and multiply this with this weight. In this case, we would have 2 antecedents, so we would take 1 over 2 and multiply it with this weight and also add it to the rule priority. But in this case, it's 0 and we don't do anything. But the user could specify that he wants this, and in machine learning in general, it's fairly common to say that simpler rules are better. So why not? The whitelisting says that we really want our whitelist weights that we added ourselves in the output, if we have any. So this would multiply 1 times 1,000 for every rule that is in the whitelist and add that. And for every other rule, this would just not do anything. For the lasso configuration, this is a very vital part, and you might have to do some trial and error before you compute the p-values, since you could over-regularize stuff and get to underfitting, or do too many iterations and get to overfitting. So this is a bit of a trial and error region. Lasso regularization is it's an iterative process because there's no closed-term solution. So it's a bit tricky to get this right, and it might take you a few tries. Having a high regularization parameter here enforces sparseness. So you would have few parameters a few rules in the output, few basis functions would get weights, and here it says how hard will you try to reach an optimum. Again, this could yield a bad fit if you try too hard here, so to say. So essentially, if you want to remove insignificant rules and this is ticked, then you might want to refit the coefficients. So this is one method to do it. Also, rules with a coefficient of 0 are often not shown because they're regularized away by lasso. And if they've got a coefficient of 0, also optimizes for sparseness, remember. So then there's no meaning in this rule. Essentially, then it has no weight. So why would we show it? And it will be shown in the warnings. And also the rules which are removed by rule priority filtering. So we compute this rule priority. And if it's not at least as important as we would like it to be with this minimum priority, this is also something to play around with. Then we're just going to remove the rule, because there's no point in looking at the rule without any theoretical influence. Only make the lasso regression harder and take more time. So it's a good optimization to be rather restrictive here. Right, next up, the outlier filtering. This should be especially applied to the target variable. In this case, it's the salary. And so you can set the column name, you can set interquartile range, for example. So if you set the interquartile range, then you will drop everything outside of this factor times the interquartile range, like with default box plots, which is often done. But if you know your data well, you can just set min and max, and in case you import the data, you will also get a neat little histogram below here, where you can choose your upper and lower bounds for removing data, which is also shown in the warnings here. Remove 13 rows. Why would you want to remove outliers? Well, outliers are really influential in regression, and you want a general tendency. You don't want the 13 outliers to heavily determine your regression results. You want the other 3001 minus 13 data points, or actually it's 3000 because there's one line which is only the header. So you want the other 3000 rows to be really influential, and you want to use them to see a general tendency. And last but not least, you can remove columns with a low variance in the dataset. This would be the option to go. And here you can set the threshold. Since if you've got a column with no variance, then it's not going to explain anything really about the target variable. Okay, now as I promised, let's now lastly look at the warnings. Already explained the first one. Then we have no duplicate columns. This is good. And to duplicate columns would indicate that the rules are the same. Means that they have the same values. Then priority decides which rule is named. So actually they represent the same numerics across all the samples, but in essence they have different titles and different names. So there might be overlaps, and we also state the overlap later in the warnings. This is also in more detail explained on GitHub. There's a few predictors removed as they have no variance, essentially. And this means if there's like a rule that is never active, why would we analyze it? So there's no need in analyzing it, so we immediately remove it. And then there's rules which are removed by priority filtering, so the priority was too low. This is essentially really good to get rid of many. And hereby I invite you to join the discussion by the project on GitHub. You can just run it in your browser, and it should work in any modern browser like Firefox, Chrome, Opera, you name it. Once the paper's up, I will state it here, and if you've got any questions, feel free to get in touch with me or to create a GitHub issue in the case you find any issues. Right? Thanks for watching, and bye.